The entire sky is filled with a ghostly, invisible light. This is the cosmic gamma ray background, a faint fog of the universe's most energetic radiation that comes from every direction we look. It is not the light of stars or galaxies you can see, but a pervasive whisper of gamma rays, the kind produced in the most violent events imaginable. Yet, its true source remains one of astronomy's greatest unsolved puzzles. It is like trying to hear a single quiet conversation in the middle of a roaring hurricane. By the end of this exploration, you will understand the 25 most compelling mysteries that make this background glow so profoundly strange. Is it the combined light of trillions of hidden black holes, or could it be the first faint signal of invisible dark matter itself? The answer is written across the entire sky if only we can learn to read it. What do you think is the most likely source of a cosmic whisper? This faint glow is the first and most fundamental mystery. Its very nature defies a simple answer. We are not looking at a collection of distinct, brilliant points of light like stars in a night sky. Instead, it is a perfectly smooth, uniform fog. This tells us the source is either incredibly numerous or fundamentally different from anything we can see directly. Imagine listening to a vast crowd from a great distance. You hear a constant collective roar, but you cannot pick out the voice of any single person. That is precisely the challenge astronomers face. They are hearing the cosmic roar of gamma rays, but the individual voices are lost in the crowd. So, who is in this crowd? The leading suspect is a colossal population of incredibly distant and faint active galaxies, known as pulsars. At the hearts of these galaxies are supermassive black holes, feasting on surrounding matter and blasting out twin jets of radiation. If one of those jets is pointed almost directly at Earth, we see it as a brilliant, variable beacon of gamma rays. The theory suggests that the combined, unresolved light from trillions of these pulsars across the entire history of the universe could be what creates the diffuse background we see. It is a census of cosmic violence summed up into a single, quiet whisper, but there is another, far more tantalizing possibility. What if this glow is not from black holes at all, but from the universe's greatest ghost? Dark matter, the invisible substance that makes up most of the mass in the cosmos, could be the source. Some theories suggest that when two particles of dark matter collide, they might annihilate each other, transforming their mass into a flash of gamma rays. If this happens everywhere dark matter exists, which is essentially everywhere, then these countless, tiny, invisible flashes could add up to create the very background we detect. The problem is one of cosmic forensics. With our current telescopes, the gamma-ray fog looks the same whether it is made by a trillion faint pulsars or a quadrillion dark matter annihilations. Distinguishing between a universe filled with hidden monsters and a universe filled with self-destructing ghosts is perhaps the greatest observational challenge in modern astrophysics. This leads us directly to the second great mystery, a puzzle astronomers call the missing pulsar problem. Pulsars are among the most powerful and terrifying objects in the universe. Imagine a supermassive black hole, millions or even billions of times heavier than our Sun, sitting at the center of a galaxy. As it devours matter, it does not do so quietly. Some of that material gets channeled into two incredibly focused beams, or jets, of particles and radiation that shoot out from its poles at nearly the speed of light. If our solar system happens to be staring directly down the barrel of one of those jets, we see that galaxy as a pulsar, a lighthouse of pure cosmic fury. For years, the leading theory was beautifully simple. The faint, uniform gamma-ray glow blanketing the sky must be the combined light of all the pulsars too distant and too dim for our telescopes to see individually. It was a cosmic background hum created by countless invisible monsters, all pointing their deadly beams in our general direction. But when scientists finally tallied up all the blazars they could see with instruments like the Fermi Gamma Ray Space Telescope and carefully calculated how many more should be hiding in the fog, the numbers came up short. The models predicted that blazars should account for almost all of the mysterious background glow. The reality is starkly different. The best estimates now suggest that all the blazars in the universe, both the bright ones we see and the trillions of faint ones we infer, can only explain about half of the gamma-ray fog. This is a profound discrepancy. It means that even after we account for every single one of these cosmic lighthouses, a full half of the universe's most energetic light remains completely unaccounted for. The background is twice as bright as it should be, so what is producing the other half of this glow? Something else, something fundamentally different, must be flooding the cosmos with gamma rays. This missing signal forces us to look beyond the obvious monsters, toward sources we have not yet fully imagined or detected. The universe, it seems, is keeping a second, even deeper secret. This missing half of the gamma-ray fog points toward a shadowy suspect, one that makes up most of the universe yet has never been seen. The second leading theory is far more tantalizing, and it connects the glow to the cosmos's greatest ghost, dark matter. For decades, physicists have searched for this invisible substance that holds galaxies together. One of the most promising candidates is known as a WIMP, a weakly interacting massive particle. True to its name, a WIMP would rarely interact with normal matter, passing through our planet and our bodies as if they were not even there. But there is a captivating possibility. Some theories suggest that when two WIMP meet, they could annihilate one another, converting their mass directly into a burst of pure energy, including gamma rays. Think of it like this. Imagine a universe filled with countless invisible fireflies that never emit light. But if two of these dark fireflies ever collide, they vanish in a tiny, brilliant flash. If this is happening everywhere dark matter exists, which is essentially everywhere, then these countless, invisible flashes could collectively create the very background glow we detect. The hunt, then, becomes a search for a specific signature within the fog. Not all gamma rays are created equal. They come with different energies, like notes in a cosmic song. Most astrophysical processes, like blazar jets, produce a broad, messy smear of energies, a cacophony of sound. But a dark matter particle annihilating would produce gamma rays at very specific, predictable energies, a single pure note ringing out. For a brief, thrilling moment, data from the Fermi telescope hinted at just such a note. A faint line in the gamma-ray spectrum at an energy of 130 gigaelectronvolts. It was the potential whisper of a specific dark matter particle, a possible fingerprint left in the cosmic background. The excitement was palpable, but the note proved elusive. Further analysis and more data could not confirm it. The signal faded back into the noise, a reminder of the monumental challenge. Confirming a dark matter signal within the gamma-ray background is the ultimate cosmic needle in a haystack search. You are looking for one pure, faint musical note within a roaring symphony of astrophysical processes. You must distinguish the signal of a ghost from the combined light of every black hole, pulsar, and stellar explosion in the universe. It requires not just better telescopes, but a deeper understanding of every other possible source of gamma rays to rule them all out. The background is not just a mystery to be solved, it is a potential message waiting to be decoded. While the search for dark matter continues, astronomers must also examine more ordinary, yet equally violent cosmic neighborhoods. Beyond the focused beams of blazars, there is another powerful source of gamma rays hidden within the very fabric of star-forming galaxies. Think of a galaxy like our own Milky Way, but in a state of frenzied creation. In these stellar nurseries, massive stars are born, live fast, and die young in colossal supernova explosions. Each of these explosions acts as a natural particle accelerator, launching protons and atomic nuclei known as cosmic rays at nearly the speed of light. These cosmic rays then race through the galaxy, smashing into the clouds of gas and starlight that fill the space between stars. When such a high-speed collision occurs, it can produce a cascade of secondary particles and ultimately a flash of gamma-ray light. This means that every galaxy actively making stars is also, in a sense, glowing faintly in gamma rays. It is the diffuse light of a million cosmic car crashes happening every second. These star-forming galaxies are everywhere in the universe, far more common than the rare and exotic blazars. So could their combined faint glow be the missing piece of the puzzle? Could they account for the half of the background that the blazars cannot explain? The challenge is one of collective faintness. While a single star-forming galaxy produces far more gamma rays than our quiet Milky Way, it is still incredibly dim compared to a blazar pointed right at us. It is like comparing the collective light of a million fireflies scattered across a valley to the beam of a single spotlight. To test this idea, scientists use a clever technique called stacking. Since they cannot see the gamma-ray glow from any one distant star-forming galaxy, they take the known positions of thousands of them from other telescopes. They then add or stack all the faint gamma-ray signals from those precise spots in the sky. It is a statistical method to amplify a whisper into a detectable voice. The results are intriguing but not yet definitive. These galaxies do contribute to the cosmic background, there is no doubt, but the critical question is how much. Current estimates suggest that while they are a significant player, they likely still cannot fill the entire gap left by the missing blazars. They add another instrument to the cosmic orchestra, but the symphony still feels incomplete. This leaves us with a growing catalogue of contributors, each important but none sufficient on its own. The background is beginning to look less like the product of a single dominant source and more like a cosmic chorus with many different voices singing together. But if blazars, star-forming galaxies, and perhaps dark matter are all singing, why does the total volume of their song still not match what we hear? The search must widen to even stranger and more elusive performers. Deep within the star cities of the cosmos, another kind of lighthouse is blinking, one far older and more precise than any blazar. These are millisecond pulsars, and they add a fascinating new layer of complexity to the gamma-ray fog. Picture the corpse of a massive star, a neutron star, compressed into a sphere just a dozen miles across yet weighing more than our sun. It is a city-sized diamond spinning hundreds of times every second, with beams of radiation shooting from its magnetic poles like a cosmic strobe light. When those beams sweep across Earth, we see a pulse of light with a regularity that rivals the most accurate atomic clocks. Our own Milky Way galaxy is home to many of these incredible objects, especially in its crowded central bulge and in the ancient, dense balls of stars known as globular clusters. Fermi has detected gamma rays from many of them, proving they are potent if individual sources of this high-energy light. But here is where the mystery deepens. Could a vast population of these faint, distant pulsars, hidden in the hearts of other galaxies, be collectively contributing to the smooth, extragalactic background we see? Each one would be far too dim to detect across intergalactic space, but together, their combined steady leakage of gamma rays might be significant. It is like trying to measure the light from a distant forest. You cannot see any single tree, but the collective glow of billions of leaves can create a visible haze on the horizon. The challenge for astronomers is quantifying this. How many of these stellar cinders are out there, spinning silently in the dark? Their gamma-ray beams are narrow, so we only see the ones pointed at us, making a true census incredibly difficult. If their numbers are vast enough, they could be a persistent, underlying component of the background, a rhythmic hum beneath the more violent crashes and explosions. This turns the cosmic chorus into something even richer, with not just the roar of black holes and the crash of supernova, but also the steady, metronomic ticking of countless dead stars, all adding their faint, precise notes to the universal symphony. The cosmic search widens from individual galaxies to the grandest structures in existence. Beyond the blazars and the star factories, the universe is woven into a vast web, with galaxy clusters sitting at its densest intersections. These are the metropolises of the cosmos, each containing hundreds or even thousands of galaxies, all bound together by the immense gravity of an unseen halo of dark matter. But the space between those galaxies is not empty. It is filled with an incredibly thin, superheated gas known as the intracluster medium, which is so hot it glows in X-rays. This environment, a swirling sea of charged particles and tangled magnetic fields, becomes a perfect arena for generating gamma rays. Within this hot gas, cosmic rays, those protons and atomic nuclei accelerated to near light speed by supernova and other violent events, can travel for billions of years. As they spiral along the cluster's powerful magnetic fields, they inevitably collide with the particles of the hot gas or the photons of ancient starlight that fill the void. Each of these collisions can produce a cascade of secondary particles and ultimately a flash of gamma-ray light. So every massive galaxy cluster could be a faint, diffuse source of this high-energy radiation glowing from the inside out. The question for astronomers is whether this glow is significant on a universal scale. If you add up the potential gamma-ray emission from every single galaxy cluster across the entire observable universe, would it create a smooth, detectable layer in the cosmic background? Or is it simply too faint, washed out by the brighter signals from blazars and star-forming galaxies? The challenge is one of extreme subtlety. While a single, nearby galaxy cluster might emit a faint whisper of gamma rays, detecting that whisper from the distance of billions of light years is currently at the very limit, or even beyond the limit of our telescopes. It is like trying to hear the hum of a single power line from the other side of a roaring city. Scientists use sophisticated models to predict the collective output, but confirming it observationally is a monumental task. Initial studies suggest that while clusters do contribute, their total signal is likely a minor component of the overall background fog, perhaps just a few percent. They are another instrument in the cosmic orchestra, but one that plays a very soft, sustained note. This finding is crucial, however, because it helps us rule things out. By determining what the background is not, we slowly close in on what it must be. If galaxy clusters are only a faint contributor, then the search for the missing half of the glow must press on, leading us to consider even more exotic and energetic phenomena. This brings us to a sharp and specific anomaly within the fog, a spectral fingerprint that does not quite fit. While the overall glow is mysterious, its behavior at the very highest energies is particularly strange. Scientists call this the high-energy excess. When astronomers carefully measure the gamma-ray background, they find that its intensity at energies above about 50 gigaelectronvolts is noticeably brighter than many of our best models predict. It is as if the cosmic symphony has a section of instruments playing much louder than the sheet music says they should. This is not just a question of volume, but of tone. Gamma rays at these energies are the most penetrating and powerful, born from the most extreme processes. Their excess suggests that something out there is producing more of these ultra-high-energy photons than our catalog of known sources can account for. One possibility is that our understanding of blazars is still incomplete. Perhaps there exists a hidden population of these monsters that are even more powerful, or that operate in a different way, preferentially generating this hard, piercing radiation. Maybe the environments around their jets are more efficient particle accelerators than we thought, slinging particles to even greater speeds and creating more of these high-energy photons in the collisions that follow. Another avenue points to an entirely different class of source we have not yet properly considered. Could it be linked to the tumultuous environments around supermassive black holes that are not pointed directly at us, or to vast, magnetized structures in intergalactic space? Or, most intriguingly, could this excess be a subtle sign of new physics, Some theories of dark matter predict that heavier particles, when they annihilate, would produce gamma rays predominantly at these very high energies. The excess could be a faint but real signal, the spectral signature of a specific type of dark matter particle finally revealing itself in the data. This is where the future of the hunt becomes incredibly exciting. Our current flagship, the Fermi telescope, has mapped the sky brilliantly, but at these extreme energies, its vision starts to blur. To see clearly, we need a new kind of eye on the sky. Enter the next generation of observatories like the Cherenkov Telescope Array. This ambitious project will not look for gamma rays directly from space, but will instead detect the fleeting flashes of blue Cherenkov light that these gamma rays create when they strike Earth's atmosphere. It is a ground-based observatory designed to catch the aftermath of the universe's most powerful photons. With sensitivity dozens of times greater than current instruments at these high energies, the Cherenkov Telescope Array will effectively turn up the volume on this specific part of the cosmic symphony. It will listen for the loud, high notes with unprecedented clarity, hoping to pick out individual sources from the haze or to see if the excess forms a specific pattern across the sky. This is not just about adding another instrument to the orchestra. It is about finally being able to hear the individual musicians playing the most difficult passages. The high-energy excess is a precise clue, a deviation in the data that points a finger toward a specific corner of cosmic possibility. Solving it could mean discovering a new breed of celestial powerhouse, or it could be the first hard evidence of a shadow universe made of dark matter, finally making its presence known not with a bang, but with a persistent high-energy whisper. This remarkable smoothness presents its own profound puzzle, the isotropy enigma. If you look at a map of the cosmic gamma ray background, the most striking feature is not a pattern, but the lack of one. It appears almost perfectly uniform, a featureless fog with no bright spots, no dark voids, and no discernible structure. This is deeply strange because we know the universe itself is not smooth. On the largest scales, matter is clumped into a vast cosmic web, a labyrinth of galaxy clusters, long filaments, and enormous empty bubbles. The distribution of galaxies and the dark matter that guides them is fundamentally lumpy. Yet the gamma-ray fog ignores this entirely. It paints the sky with a single, even brushstroke. This uniformity forces a critical conclusion upon us. Whatever is producing this glow must be either unimaginably numerous or fundamentally different from the discrete structures we see. Think of it like the sound of rain on a roof. From inside, you hear a constant, steady roar. You cannot hear any individual raindrop because there are simply too many of them, all contributing equally to the overall sound. The gamma-ray background could be exactly that, the combined roar of trillions upon trillions of faint sources, like blazars or star-forming galaxies, so evenly scattered across the cosmos that their light blends into a seamless haze. Their sheer number would wash out any trace of the universe's underlying lumpiness, but there is another, more radical interpretation. What if the glow is not from countless individual sources at all, but from a truly diffuse process? Imagine the air in a room glowing with a faint, even light because of some chemical reaction happening within the air itself, not because of many tiny light bulbs scattered around. In cosmic terms, this could point to processes that fill the space between galaxies. Perhaps it is the cumulative effect of dark matter annihilations occurring uniformly throughout the vast halos surrounding every galaxy and filament. Or maybe it is the sum of countless interactions involving cosmic rays and ancient light in the truly intergalactic void. The isotropy is a powerful constraint, a rule that every potential solution must obey. Any model that claims to explain the gamma-ray background must also explain why it looks the same in every direction, despite the universe's obvious clumpiness. This smoothness is not a minor detail, it is a central clue, whispering that the truth behind the glow is either astonishingly abundant or seamlessly woven into the fabric of space itself. The smooth, uniform glow presents another layer of contradiction when we compare it to the rest of the cosmic light show. This is the mystery of the missing correlation. If the dominant sources of the gamma-ray fog were ordinary astrophysical objects like blazars or bustling star-forming galaxies, we would expect a specific pattern to emerge. The gamma-ray sky should look somewhat similar to the sky mapped in other forms of light, like X-rays or infrared. These objects are not one-trick ponies, they shine across many wavelengths simultaneously. A distant blazar, for instance, should be a bright dot in gamma rays and a corresponding bright dot in radio waves. So, if you took a map of the radio sky and a map of the gamma ray background and overlaid them, you would anticipate the bright patches and the faint patches to roughly line up. They do not. The correlation is far weaker than the simplest models predict. It is as if you listened to an orchestra with your eyes closed, and you could clearly hear the violins and the trumpets, but when you opened your eyes, the violinists were in one corner and the trumpet players were scattered randomly around the room. The sound is coming from the right general area, but the specific sources are not matching your expectations. This discrepancy forces a profound rethink. It suggests that the objects primarily responsible for the gamma-ray background are either not the same ones dominating these other wavelengths, or they are in a different state. Perhaps the gamma rays are coming from a population of blazars that are, for some reason, unusually quiet in radio waves. Maybe they are in an early or late stage of their life cycle, where their jets produce gamma rays efficiently, but not the other emissions we typically associate with them. Or it could point to something entirely different. The weak correlation is a clue that we may be searching for the wrong suspects. It opens the door for more obscure source populations that are gamma-ray bright but faint or invisible in every other part of the spectrum we can observe. What kind of cosmic object shines only in the most extreme, penetrating light and hides from all others? The answer to that question might finally explain the ghostly, uniform fog that has puzzled astronomers for decades. The universe's most violent deaths may also leave behind a faint, collective echo. Beyond the steady glow of black holes and star factories, there are events of unimaginable, instantaneous fury, gamma-ray bursts. These are the birth cries of black holes, the final screams of massive stars collapsing in hypernova explosions so powerful they can outshine an entire galaxy for a few fleeting seconds. For a long-duration burst, the main event is over in minutes, but its aftermath, a fading afterglow that radiates across many wavelengths, can persist for days or even weeks. This afterglow is the dying star's final signature, a fading ember of its catastrophic end. So, could the combined light of countless such embers, from bursts that flashed across the cosmos over billions of years, contribute to the smooth gamma-ray fog we see today? It is a compelling idea to think the background might be a cosmic graveyard, illuminated by the fading afterglows of stellar deaths from eons past. To test it, we must run the numbers, a grim but necessary cosmic accounting. Astronomers can estimate how often these catastrophic events occur in a given volume of the universe over its history. They can also measure the typical energy output of a burst's afterglow in the gamma-ray part of the spectrum. The question is simple: does the math add up? If you take the total number of stars that have died in such spectacular fashion since the beginning of time and sum up all their fading gamma-ray light, would it create a detectable, uniform background? The calculations point to a sobering answer: likely not. While gamma-ray bursts are phenomenally bright, they are also incredibly rare. A large galaxy like our Milky Way might host one such event only every few 100,000 years or so. Across the vastness of the observable universe, this means that at any given moment, the number of fading afterglows is simply too small to create a seamless, fog-like glow. The individual embers are too far apart and too few in number. Their contribution is more like a handful of distant, scattered campfires on a vast, dark plain, not the uniform illumination of a city's light pollution. They add a faint, sporadic sparkle to the cosmic background, but they cannot be its primary source. This realization is crucial as it forces us to cross another potential suspect off the list. The gamma-ray background is not the lingering echo of the universe's most famous explosions. Its source must be something more constant, more ubiquitous, and perhaps even more strange. The very first moments of the universe might be hiding within the gamma-ray fog. This leads us to one of the most speculative and fascinating possibilities, the potential fingerprint of primordial black holes. Unlike the supermassive giants at the centers of galaxies, these would be tiny, ancient relics, perhaps no heavier than a mountain yet compressed into a space smaller than an atom. They are thought to have formed not from dying stars, but from the intense density fluctuations in the chaotic soup of the newborn cosmos. According to Stephen Hawking's revolutionary theory, black holes are not truly black. They should slowly leak energy, a process known as Hawking radiation. For a massive black hole, this evaporation is immeasurably slow, a faint sigh over trillions of years. But for a tiny primordial black hole, the story is dramatically different. Its small size means it evaporates at a furious pace. In the final, explosive instant of its existence, such a black hole would vanish in a spectacular burst of energy, releasing a flash of gamma rays as its final signature. Now, imagine a universe that once teemed with countless numbers of these tiny, ticking time bombs. If they were common in the early cosmos, then across time and space, an uncountable number would have reached their end and detonated. Each one a microscopic Big Bang in reverse. The collective flash of all those evaporations spread across billions of years could have left a faint, diffuse afterglow woven into the very fabric of the gamma-ray background we see today. This is not just about adding another source to the list, it is about using the background as a time machine. The specific energy signature of those final bursts would carry information about the mass of the original black holes, which in turn tells us about the conditions of the universe when they were born. Finding their spectral imprint would be like discovering fossilized ripples from the first second of creation. It would offer direct, observational evidence for physics at energies far beyond anything our particle colliders can ever achieve, a window into an era that is otherwise completely inaccessible. So far, searches for this specific signal have come up empty. The smooth background shows no clear bump or spike that neatly matches the predictions for evaporating black holes of a certain mass. But the hunt is far from over. The null result is itself a profound clue. It tells us that if these primordial black holes exist, they cannot be numerous enough to dominate the gamma-ray sky. They might be a rare component, their whisper drowned out by the roar of blazars and star-forming galaxies. Or perhaps they evaporate in a way we do not yet fully understand. The mystery of the primordial black hole is a perfect example of how the cosmic gamma-ray background is more than a puzzle. It is a canvas. On it, we can test our wildest ideas about the origin of everything, searching for ghosts from the universe's first breath. The gamma-ray glow from a star-forming galaxy is not a simple light. It is a byproduct of a hidden engine. That engine is the relentless fury of supernova. When a massive star ends its life in a cataclysm, it does more than just scatter its elements into space. It acts as a natural particle accelerator. The shock wave from the explosion can fling protons and atomic nuclei to almost the speed of light, creating a flood of cosmic rays. These high-energy particles then race through the galaxy, trapped by its magnetic fields. Their journey is a violent one, as they constantly collide with the atoms of the thin gas and the sea of starlight that fills the space between stars. It is from these brutal, microscopic collisions that the gamma rays are born, a secondary flash of light from a primary event of destruction. So, the gamma-ray luminosity of a galaxy becomes a direct measure of its cosmic ray activity, a gauge of how many stellar explosions are happening and how effectively they are turning their energy into this penetrating radiation. This leads us to a critical and thorny puzzle known as the calorimetry problem. In simple terms, calorimetry asks how good is a galaxy at trapping these cosmic rays. Imagine a pot of water on a stove. If the pot has a tight lid, the steam is trapped, the pressure builds, and the water gets hotter efficiently. But if the lid is loose or full of holes, the steam escapes and much of the energy is lost. A galaxy is like that pot, and its magnetic fields are the lid. In a galaxy with strong, tangled magnetic fields, cosmic rays bounce around for a long time, making countless collisions and producing lots of gamma-ray light before they can finally escape into intergalactic space. This galaxy is an efficient calorimeter, converting a large fraction of its supernova energy into gamma rays we might detect. But another galaxy might have weaker magnetic fields or a more porous structure with vast chimneys blowing material out into the void. In that case, the cosmic rays can leak out quickly, like steam through a sieve, carrying their energy away before it can be turned into gamma rays. This galaxy is a poor calorimeter. The problem for astronomers is that we cannot easily measure this efficiency from a distance. Looking at a faint, distant galaxy, we see the total starlight and can estimate its star formation rate, but we have no simple way to know how strong its magnetic lid is. This variation in calorimetric efficiency from galaxy to galaxy creates a huge uncertainty when we try to sum up their total contribution to the cosmic background. We know the ingredients, the supernova, but we do not know the exact recipe for each kitchen. Our best estimates for the collective gamma-ray output of all star-forming galaxies therefore come with a wide range, a band of possibility. They could be a major player or they could be a modest one. This intrinsic uncertainty is why, even as we add them to the chorus alongside blazars, the total volume of the cosmic symphony still feels like it has a missing section. The background glow is a precise measurement, but one of its most likely sources remains frustratingly fuzzy. Its true strength hidden behind the variable and invisible magnetic walls of a trillion different galactic homes. The challenge of the missing blazars forces us to reconsider our entire view of cosmic powerhouses. Active galactic nuclei are not a monolith, they are a diverse family with one terrifying parent, a supermassive black hole. Our view of them depends entirely on our perspective. The spectacular blazars we have discussed are just one type, the rare ones where we stare directly down the barrel of a relativistic jet. But for every galaxy with a jet pointed at Earth, there are hundreds or thousands more where the jet is pointed in any other direction. These are the Seyfert galaxies, the radio galaxies, the quasars seen from the side. From our skewed viewpoint, we see their brilliant accretion disks and glowing gas clouds, but their most powerful particle beams are shooting off into the darkness, missing us entirely. For decades, astronomers have used a powerful concept called the unification model to explain this diversity. It proposes that all these different-looking active galaxies are fundamentally the same object, a supermassive black hole with an accretion disk and jets, but viewed from different angles. It is like seeing a flashlight from the front, the side, or from behind. The light looks different, but the source is identical. This model is brilliantly successful at explaining what we see in optical and radio light. But when we apply it to the gamma-ray sky, a new tension emerges. If the unification model holds true, then all those misaligned active galaxies, the ones with jets pointed away from us, must also be producing gamma rays. Their jets slamming into the intergalactic medium or their own galaxy's gas should create shockwaves that generate this high-energy light. So, the obvious solution to the missing source problem seems to be right in front of us. Perhaps we have simply been underestimating the gamma-ray choir by only counting the soloists singing directly at us. By adding in the collective hum from all the other active galaxies viewed from the side or rear, could we finally account for the full intensity of the cosmic background? The answer, frustratingly, is complex and incomplete. Initial attempts to fold these populations into the models do help, but they do not solve the puzzle outright. Including the gamma-ray emission from misaligned jets does add more light to the fog, but it also introduces new questions. We must accurately estimate how many of these galaxies exist, how powerful their jets are, and crucially, how efficiently those sideways jets convert their energy into the gamma rays that eventually scatter our way. The data is sparse because by their very nature, these objects are much fainter in gamma rays than blazars. We are trying to measure the faint, reflected glare from a cosmic lighthouse whose main beam is pointed away from us. Furthermore, if these other active galaxies were pouring out enough gamma rays to fill the gap, we might expect to see other telltale signs, like a specific correlation with large-scale cosmic structures that host them, or a different spectral shape in the background. So far, those predicted signatures remain elusive. The unification model challenge reveals a deeper truth. The universe is not making it easy. Even when we try to account for every single active black hole in every possible orientation, the ledger still may not balance. This suggests the solution might not lie in simply finding more members of a known family, but in discovering an entirely new family of gamma-ray sources we have not yet met. This journey across the cosmos introduces a surprising twist, a cosmic fog that acts not as a source of light but as a veil. Even the most powerful gamma rays cannot travel forever unscathed. On their billion-year journeys from distant blazars, they must pass through a sea of ancient starlight known as the extragalactic background light. This EBL is the collective glow of every star that has ever shone, a faint, omnipresent radiation field that fills the space between galaxies. It is the ultimate family photo of the universe, a sum total of all stellar creation. When an ultra-high-energy gamma ray, a single particle of light, encounters one of these much lower energy photons from the EBL, something remarkable can happen. If the collision is just right, the two can annihilate each other, transforming their energy into matter, specifically an electron and its antimatter counterpart, a positron. In that instant, the original gamma ray vanishes. This process, called pair production, acts like a cosmic filter, selectively absorbing the very highest energy gamma rays coming from the most distant reaches of space. The farther a gamma ray has to travel, the more likely it is to meet this fate. This means the gamma ray background we measure is not a pure signal. It is a filtered one, subtly shaped by the very history of starlight it passed through. But here is where a problem becomes a powerful tool. By carefully analyzing the spectrum of the gamma ray background, particularly how its intensity drops off at the highest energies, astronomers can actually measure the density and evolution of the extragalactic background light itself. They are using the absorption of gamma rays to illuminate the history of stars. It is like figuring out how thick a fog is by measuring how much a distant lighthouse beam has dimmed. This turns the gamma ray background from a mystery to be solved into a unique telescope for studying the universe's entire history of star formation. The faint attenuation we see in the data is a direct imprint of every galaxy's light across all of cosmic time. By decoding this imprint, we can ask profound questions. When did most of the stars in the universe form? Is our census of galaxies from optical telescopes missing a vast number of faint, early stars? The gamma-ray fog, by being partially absorbed, carries within it the ghostly signature of all the light that ever was. Our own galactic home holds a clue to this cosmic puzzle. In the heart of the Milky Way, astronomers discovered two colossal, ghostly structures, each towering 25,000 light-years above and below the galactic plane. These are the Fermi bubbles, immense lobes of gamma-ray light that look like a giant, cosmic hourglass centered on our supermassive black hole. They are the aftermath of a past eruption, a titanic burp of energy from Sagittarius, a star that blasted high-energy particles into intergalactic space, where they now glow faintly in gamma rays. This discovery was a revelation, proving that our own galaxy is not a quiet island, but a place with a violent, dynamic history written in high-energy light. And that leads to a profound question. If our Milky Way has these structures, why wouldn't other galaxies? Every spiral galaxy likely hosts its own supermassive black hole, and many of those may have experienced similar eruptions in their past. Imagine a universe where every major galaxy is surrounded by its own pair of faint gamma-ray balloons, its own set of Fermi bubbles. From our distant vantage point across millions of light years, we would never see the individual hourglass shape. Those colossal structures would be far too dim and extended to resolve as anything more than a faint, fuzzy halo of light around an already faint galaxy. And if we cannot see them individually, what would we see? The combined light of 1 trillion such galactic halos, all overlapping from every direction in the sky, would blend together into a perfectly smooth, uniform fog. It could be the ultimate cosmic background, woven from the faded echoes of black hole outbursts from every corner of the universe. This idea transforms the gamma-ray fog from a mystery into a potential family portrait. It would be a collective image of galactic adolescence, a sign that growing black holes go through energetic tantrums, blowing giant bubbles that linger for eons. Searching for this signature, however, is a monumental challenge. It requires looking for the most subtle correlations. One approach is to stack the gamma-ray data from the positions of millions of known quiet galaxies, similar to our own Milky Way, to see if there is an excess of diffuse emission extending far beyond their visible edges. Another is to look for a specific pattern in the background spectrum that matches what we see from our own Fermi bubbles, a particular blend of energies that points to particles cooling in a magnetized halo. Finding even a hint of this would be a cosmic revelation. It would mean the faint glow we see is not just about creation or annihilation, but about breathing. It is the universe slowly exhaling, the collective sigh of 1 billion black holes, each having blown its own bubbles into the dark. Beyond the boundaries of galaxies lies the greatest wilderness of all, the vast and seemingly empty intergalactic void. Yet this space is not truly empty. It is threaded with invisible forces and flooded with ancient light. Here, a subtle process could be contributing to the cosmic gamma-ray fog, one that depends on a hidden cosmic architecture. When cosmic rays, those protons and nuclei accelerated to near light speed within galaxies, finally escape their galactic confines, they do not simply vanish. They stream out into the intergalactic medium, embarking on journeys that can last for billions of years. In this profound emptiness, they encounter the diffuse sea of the extragalactic background light, the accumulated starlight of the universe. When an ultra-high-energy cosmic ray collides with one of these low-energy photons, it can produce a new particle, a pion, which then rapidly decays into a pair of gamma rays. This means the space between galaxies itself could be faintly glowing, a product of escaped particles from 1 trillion galactic accelerators crashing into the ghost of ancient starlight. The intensity of this glow, however, hinges on a deeply mysterious factor, the strength of intergalactic magnetic fields. These are not the organized fields of a galaxy, but faint, tangled webs stretching across the cosmic void. They are incredibly weak, perhaps 1 billion times weaker than Earth's magnetic field, but they are thought to be everywhere. Their role is crucial because they control the journey of the cosmic rays. Stronger intergalactic magnetic fields would trap the escaping particles, making them bounce around and travel a much longer, more tortuous path before they finally reach us. This longer journey increases the chance they will collide with background light and produce gamma rays along the way. Conversely, if the magnetic fields in the voids are very weak or patchy, the cosmic rays would travel in nearly straight lines, making fewer interactions and producing a fainter intergalactic glow. This turns the gamma-ray background into a potential probe for the invisible. By carefully measuring the spectrum and smoothness of the fog and comparing it to models of cosmic ray escape, scientists could, in theory, infer the strength and structure of these elusive magnetic fields woven through the cosmic web. It is an audacious idea, using the faintest light in the universe to map forces 1 billion times weaker than a common refrigerator magnet. The challenge is immense as the signal is buried under all the other contributors, but the promise is extraordinary. It would mean that the cosmic gamma-ray background is not just a puzzle to solve, but a unique instrument, a lens through which we can see the magnetic skeleton of the universe itself. The hunt for a pure note within the cosmic symphony defines one of the most focused quests in modern physics. While a smooth excess of gamma rays could point to dark matter, it could also be explained by astrophysical sources. A true smoking gun would be something far more specific, a sharp, narrow spike at one exact energy in the gamma ray spectrum. This is the annihilation line. The principle is beautifully simple. If two identical dark matter particles collide and annihilate, converting all their mass directly into energy, Einstein's famous equation tells us the energy of the resulting gamma rays would be precisely equal to the mass of one of those particles. It would be a single, pure note ringing out across the universe, a direct broadcast of the particle's identity. Finding such a line would be an unambiguous discovery, not just telling us dark matter exists, but revealing its exact mass and confirming its particle nature. It would be like identifying a chemical element by the unique color of light it emits. The search for this spectral fingerprint is a monumental exercise in statistical archaeology. Scientists take the vast catalog of gamma-ray photons collected by telescopes like Fermi and sort them by energy with incredible precision, creating a spectrum of the entire sky. They are looking for a tiny, statistically significant bump rising above the smooth, messy continuum produced by all the blazars, pulsars, and supernova. The challenge is staggering. You are searching for a faint spike that might be only a few photons tall, buried in a background of billions. It is the ultimate needle in a haystack, where the haystack is the entire history of cosmic violence. Every potential signal must be scrutinized to rule out instrumental effects, statistical flukes, or unknown atomic processes in the interstellar medium. The community experienced this tension firsthand with a tantalizing hint at an energy of 130 gigaelectronvolts. For a time, it looked like the line might be real, sparking intense excitement and debate. But with more data and refined analysis, the signal faded, likely a cruel statistical fluctuation. This cycle of hope and rigorous doubt is the very engine of science. The null result, however, is not a failure. Each line that is not found rules out a range of possible dark matter particle masses and annihilation models, narrowing the search space. The hunt continues with ever more sensitive analyzers, peeling back the layers of the gamma-ray background, listening with increasing care for that one perfect note that would change our understanding of the universe forever. The universe's most spectacular stellar deaths are not always explosions. Sometimes they are a slow, cosmic unraveling. Picture a star like our own sun, wandering too close to the immense gravity of a supermassive black hole. The side of the star facing the black hole feels a much stronger pull than the side facing away, stretching the star into a long, thin strand of superheated gas. This is a tidal disruption event where a black hole literally pulls a star apart like taffy. As that stream of stellar material spirals into the black hole's accretion disk, it heats to incredible temperatures, producing a brilliant flare of light that can outshine its host galaxy for months. While most of this energy is seen as ultraviolet and X-ray light, a small fraction of these cataclysms also produce gamma rays, likely from jets launched during the feast. So we must ask, could these rare, one-time banquets contribute to the persistent background fog? The answer lies in the math of cosmic violence. Astronomers estimate that in a typical galaxy, a tidal disruption event happens only about once every 10,000 to 100,000 years. They are spectacular, but they are not common. Now, multiply that across the hundreds of billions of galaxies in the observable universe, At any given moment, there are still thousands of these events happening somewhere in the cosmos, each one a temporary, brilliant flare of high-energy light. The critical question is whether the gamma-ray glow from all these distant, fading flares, added together over billions of years, creates a smooth, detectable background or just a faint, sporadic flickering. The calculation is tricky because we are still learning how many of these events produce gamma rays in the first place. Only a handful have been caught doing so. If the gamma ray producing variety is extremely rare, then their collective contribution to the background is almost certainly negligible, a few scattered raindrops that do not make a fog. But if, as some models suggest, a significant percentage of tidal disruptions launch brief, powerful jets, then their combined afterglow could be a persistent, if minor, component of the cosmic hum. It would be the faint, collective echo of stars being unspooled across cosmic time. Current estimates place this contribution on the low end, likely less than 1% of the total background intensity. So while these events are crucial for understanding black hole behavior, they are probably not the missing source we are searching for. They are another fascinating instrument in the orchestra, but one that plays a solo only very occasionally, its brief, loud note quickly fading back into the steady roar of the crowd. This fundamental blurriness is not a flaw in our telescopes, but a law of physics. At gamma-ray energies, light behaves differently. The wavelengths are so incredibly short that they cannot be easily focused by mirrors or lenses like optical light. Our detectors, whether in space like Fermi or on the ground like the Cherenkov arrays, have a built-in limitation called angular resolution. In simple terms, it is the ability to tell two closely spaced points of light apart. For gamma-ray telescopes, this resolution is relatively poor. A single pinpoint of gamma-ray light in the data is actually a blurry smudge covering an area of the sky many times larger than the full moon. Now imagine the sky is filled with millions of these faint, blurry smudges. They overlap, they blend, they merge into a single, indistinguishable fog. Astronomers call this confusion noise, and it is not an error, it is an intrinsic part of the signal. It is the primary reason the gamma-ray background appears so perfectly smooth. We are not seeing a truly diffuse glow. We are seeing a forest so dense that from our vantage point, the individual trees vanish into a uniform green wall. This observational limit creates a chicken and egg problem. To prove the background is made of countless faint blazars, we need to resolve them individually. But to resolve them, we need to see through the very fog they create. Our current instruments are stuck at the edge of this confusion limit. They can see the brightest, most distinct trees at the front of the forest, but the deeper they look, the more the light from countless fainter sources blends into an unresolved haze. This is why the next generation of telescopes is not just an improvement, it is a revolution. Projects like the Cherenkov telescope array aim for an angular resolution several times sharper than current ground-based observatories. Future space-based concepts envision telescopes with vastly better focusing power. The goal is to shrink that blurry smudge down to a much finer point. With that sharper vision, the cosmic fog should begin to separate. What looks like a smooth, featureless glow today might resolve into a granular texture tomorrow, a sky speckled with millions of faint, individual dots. Each dot resolved is a mystery solved, a source identified and removed from the background ledger. Peeling back this layer of confusion noise is the most direct path to answering the fundamental question. Is the remaining glow, after every last faint blazar and pulsar is accounted for, truly empty? Or will a smooth, irreducible signal remain, pointing unequivocally towards something truly diffuse and universal like dark matter? The blurriness we struggle with today is not just a barrier, it is the veil we must lift to see the universe's deepest secret. The cosmic fog appears serene and unchanging, but this very stillness presents a new riddle. Most of the suspected sources behind it are anything but constant. Blazars, for instance, are notorious for their wild flickering, flaring up and dimming dramatically over days, weeks, or years. A star-forming galaxy's gamma-ray output might spike during periods of intense starlight and supernova. Even the processes around misaligned black holes could have their own rhythms. If the background is truly the sum of countless such variable sources, all blinking on and off at random times across the universe, then the total glow we see should have a subtle collective flicker to it. It would be like watching a city skyline from a great distance at night. You cannot see individual windows, but you might notice the overall brightness of a neighborhood pulse slightly as millions of people turn their lights on and off. Astronomers have spent years looking for this exact pulse in the gamma-ray fog, meticulously analyzing over a decade of data from the Fermi telescope to see if the background's intensity wobbles over time. The results are telling. The glow is astonishingly steady. No significant year-to-year fluctuations have been found. This profound quiet places a powerful constraint on the mystery. It tells us that the dominant sources cannot all be nearby, flickering monsters like the blazars we see clearly. If they were, their individual variations would not have enough time to synchronize or average out, and we would detect a twinkle in the fog. Instead, the lack of variability suggests the light is coming from so far away, from sources so incredibly distant, that their individual flickers are stretched and smeared by the expansion of the universe itself. Billions of years of cosmic time act as a great smoothing filter, blending countless erratic flashes into a perfectly even hum. It points toward a population of sources that are not only faint but overwhelmingly ancient, their light a fossilized echo from the universe's youth. This temporal stillness is a crucial clue, whispering that the true heart of the gamma-ray background lies not in our modern cosmic neighborhood, but deep in the formative past. The search for the sources of the universe's most powerful particles may be hidden within the gamma-ray fog. Among the countless cosmic rays filling space, there exists an elite class known as ultra-high-energy cosmic rays. These are not mere protons, they are atomic nuclei traveling with energies millions of times greater than anything our most powerful particle colliders can produce. They are nature's ultimate bullets, and we have almost no idea what cosmic cannon is firing them. Their origins are one of the greatest unsolved mysteries in physics. When one of these phenomenal particles, born in some unimaginably violent event, finally streaks through the universe, it does not travel alone. It inevitably collides with the pervasive sea of the extragalactic background light. That collision is catastrophic, producing a cascade of secondary particles, including, crucially, a burst of very high-energy gamma rays and ghostly neutrinos. This means that wherever these mysterious cosmic accelerators are located, they should also be surrounded by a faint halo of gamma-ray light, the afterglow of their most powerful emissions. So the question becomes direct and compelling. Does the gamma-ray background, especially at its most extreme energies, contain the collective fingerprint of these elusive accelerators? Is the faint, smooth fog we see partly composed of the dying echoes of the universe's most powerful particle beams? To find out, scientists must look for a specific signature. If the dominant sources of ultra-high-energy cosmic rays were something like active galactic nuclei or gamma-ray bursts, their gamma-ray afterglow would have a distinct spectral shape and would be concentrated in specific regions of the sky. The problem is that the gamma-ray background is smooth, while the arrival directions of these ultra-high-energy particles are frustratingly isotropic. They come from everywhere and nowhere specific. This suggests the accelerators are either extremely distant, their signals scrambled by magnetic fields, or they are a source we have not yet imagined. The gamma-ray background could be serving as the perfect mixing bowl, where the light from countless distant, random accelerators blends into a uniform paste. Searching for this link is a task of incredible subtlety. It requires comparing the map of the highest energy gamma rays with the sparse map of ultra-high-energy cosmic ray arrivals, looking for any faint correlation, any hint that the two mysteries share a common birthplace. So far, no definitive link has been found. The fog remains stubbornly uniform, and the particles arrive without a clear return address. This lack of a connection is in itself a profound clue. It tells us that if ultra-high-energy cosmic rays are contributing to the background, they are doing so from such immense distances that their individual sources vanish into the cosmic crowd. Their story is not written in bright, localized letters, but is instead dissolved into the universal whisper of the gamma-ray sky. The universe's magnetic fields could be hiding a particle we have never seen. Among the most speculative and elegant solutions to the gamma-ray background is a ghost from particle physics, the action-like particle. Originally conceived to solve a deep puzzle in quantum theory, these hypothetical entities are incredibly light, neutral, and would interact only very weakly with normal matter. They are, in essence, perfect cosmic phantoms, but they possess a magical property. In the presence of a strong magnetic field, an action-like particle can spontaneously transform or oscillate into a photon of light. And under the right conditions, that photon could be a gamma ray. Imagine these particles flooding the cosmos, a sea of invisible potential energy streaming through galaxies and the voids between them. Wherever they encounter the tangled magnetic fields that weave through space, a tiny fraction of them could flicker into existence as gamma-ray photons. This process would not be a violent explosion or a collision, but a quiet, continuous transmutation, like invisible ink becoming visible under a special light. If this sea of particles is real, then the entire universe is effectively one giant, faint converter, turning this hidden substance into the very glow we detect. The beauty of this idea is that it would leave a specific fingerprint. Gamma rays produced this way would carry a subtle imprint of the magnetic fields that birthed them. Scientists could search for specific patterns in the polarization of the background light, a preferred direction of vibration that points back to the magnetic fields of galaxy clusters or the cosmic web itself. The spectrum, the distribution of energies, might also show a telltale shape different from the messy continuum of astrophysical processes. Finding such a signature would be a dual discovery of monumental proportions. It would not only identify a major source of the cosmic gamma-ray background, solving a decades-long mystery, but it would also provide the first direct evidence for an entirely new class of fundamental particle, one that could also be a component of the elusive dark matter. The background fog would transform from a puzzle into a window, offering a glimpse into laws of physics that operate at energies far beyond our laboratories, written in the faint, universal light that has been shining upon us all along. That universal whisper may carry echoes from the very first dawn. To understand the deepest layer of the gamma-ray fog, we must journey back to a time before galaxies as we know them existed, to an era called reionization. For hundreds of millions of years after the Big Bang, the universe was a dark, silent sea of neutral hydrogen gas. Then the first stars ignited. These were not like the stars of today. They were behemoths, hundreds of times more massive than our sun, living ferociously brief lives and dying in titanic supernova. Their intense ultraviolet radiation began to tear apart or ionize the surrounding hydrogen fog, burning bubbles of clarity into the primordial darkness. Around these first stars, the very first black holes also formed, feasting and growing in the dense early cosmos. This period, the reionization era, was a universe-wide metamorphosis from darkness to light, and it was likely a place of staggering violence. Those first monstrous stars would have died in supernova of unimaginable power, their shockwaves accelerating the first cosmic rays. Those first black holes, feasting in the dense early gas, could have flickered to life as the earliest quasars and blazars. All of these events would have flooded their nascent cosmic neighborhoods with high-energy radiation, including gamma rays. Now, here is the profound connection. The gamma rays produced in that ancient, formative era have been traveling toward us for over 12 billion years. During that immense journey, the expansion of the universe has stretched their wavelengths, shifting them down in energy. It is like a musical note played on a piano that slowly deepens in pitch over billions of years. A gamma ray born in the death scream of one of the very first stars might reach us today not as a piercing high-energy photon, but as a lower-energy one, its original ferocity softened by time. This means the gamma ray background we measure today could be a palimpsest, a composite image where the light from the universe's violent infancy is layered underneath the light from its more recent history. We are not just mapping the sky, we are peeling back cosmic strata. Finding this fossil imprint is perhaps the ultimate challenge. It requires us to untangle a specific, ancient signal that has been stretched, diluted, and mixed with everything that came after. Astronomers look for subtle signatures, like a specific bump or dip in the background spectrum at certain energies that models predict should correspond to the output of the first stars and black holes. They also search for a specific pattern of anisotropy, a faint granularity in the fog that might correlate with the large-scale structures that were just beginning to form in that early epoch. Detecting this would be more than just solving a piece of the gamma-ray puzzle. It would be a direct observation of the universe's first lights turning on. The faint, smooth glow that blankets our sky would become a time capsule, holding within it the faded afterglow of creation's first fires. The modern hunt for the source of this cosmic fog no longer relies on a single sense. The gamma-ray background does not exist in isolation. It is one note in a much larger symphony. To truly understand it, we must listen with every instrument at our disposal, a strategy known as multi-messenger astronomy. This approach combines not just different kinds of light, but entirely different cosmic messengers, particles and waves that tell complementary stories about the universe's most violent events. Alongside the gamma-ray fog, there exists another, even more ghostly background, a diffuse sea of neutrinos detected by observatories like IceCube at the South Pole. Neutrinos are the universe's ultimate ghosts, subatomic particles with almost no mass and no electric charge, allowing them to pass through entire planets without a trace. They are born in the same catastrophic environments as gamma rays, inside the hearts of supernova or the relativistic jets of blazars. But while gamma rays can be blocked or scattered by light and magnetic fields, neutrinos travel in near-perfect straight lines from their source, offering an unfiltered view back to their origin. This creates a powerful cross-check. If the smooth gamma-ray background and the smooth neutrino background show a strong correlation, if their patterns in the sky match, it would be a landmark discovery. It would point decisively to a common source population, specifically to cosmic ray accelerators like blazars or star-forming galaxies. The logic is elegant. These environments accelerate protons to near light speed. Those protons collide to produce pions, and those pions decay to produce both gamma rays and neutrinos in a predictable pair. Finding their signals linked in the diffuse backgrounds would be like finding matching fingerprints at two separate crime scenes, confirming the identity of the culprit. The third messenger, gravitational waves, adds another dimension. These ripples in space-time itself are created by the mergers of black holes and neutron stars. While a single merger is a transient event, the combined hum from all such mergers across cosmic history could create a stochastic gravitational wave background, a universal rumble we are just beginning to detect. If a portion of the gamma-ray background were linked to these mergers, perhaps from materials swirling around the newly formed black hole, we could search for a statistical link between the gravitational wave hum and specific features in the gamma-ray fog. This multi-messenger cross-check is the future of the mystery. By layering these independent maps of the universe, we can begin to triangulate the truth. We are no longer just staring at a faint, blurry picture. We are feeling for vibrations and listening for whispers in the dark, building a three-dimensional understanding of the cosmic violence that fills the void. The final mystery is not about the past, but about the future we are building. Our current view of the gamma-ray fog is like trying to read a blurred photograph from the bottom of a deep lake. The next generation of telescopes are the tools that will finally drain the lake and bring that image into breathtaking focus. Leading this charge is the Cherenkov Telescope Array, a global observatory designed to see the universe in very high-energy gamma rays with a clarity never before possible. Instead of a single telescope, the CT will be an array of over 100 individual mirrors spread across sites in Chile and the Canary Islands. They will work together to detect the fleeting blue flashes created when gamma rays strike our atmosphere, achieving a sensitivity dozens of times greater than current instruments and a resolution several times sharper. This is the key to ending the confusion. With vision this sharp, the smooth, featureless fog should begin to separate into millions of individual points of light. We will finally see the faintest blazars, the most distant pulsars, and begin to truly census the cosmic population contributing to the haze. More importantly, the CT will examine the high-energy excess with surgical precision, searching for the spectral fingerprints of specific dark matter particles or revealing entirely new classes of cosmic accelerators hidden within the noise. But to solve a puzzle this complex, you need more than one perspective. While the CT peers into the highest energies, another revolutionary observatory will provide the essential complementary view. The Advanced Telescope for High-Energy Astrophysics, or Athena, is a space-based X-ray observatory slated for launch next decade. Why look at X-rays to solve a gamma-ray mystery? Because the same violent events often shine across both bands. Athena's extraordinary sensitivity will allow it to detect the X-ray counterparts of the faint gamma-ray sources the CT resolves. By matching them, astronomers can identify what these objects are, measuring their distances and physical conditions. This cross-identification is like finding a name tag for every faint smudge of light in the gamma-ray sky. It will tell us definitively if the fog is made of misaligned black holes, star-forming galaxies, or something else entirely, turning statistical guesses into confirmed knowledge. And the vision expands even further with concepts like the All-Sky Medium Energy Gamma Ray Observatory, or a MEGO. This proposed satellite would fill a critical gap in our observational coverage, specializing in the medium energy range where many important particle processes leave their mark. It would have the unique ability to measure the polarization of gamma rays, a property that reveals the direction of magnetic fields. This could be the tool that finally tests whether action-like particles are shimmering into existence in cosmic magnetic fields, or if the glow is shaped by the vast magnetic structures of the cosmic web. Together, these future instruments represent more than just better telescopes. They are a coordinated strategy to dissect the cosmic gamma-ray background with forensic precision. They will resolve its sources, measure its composition, and test every remaining hypothesis from dark matter to primordial black holes, with data of a quality we can now only dream of. The faint, universal whisper that has puzzled us for decades is about to be amplified. We are building the ears that will finally understand what it has been trying to say all along. This cosmic tapestry, woven from 25 intertwined puzzles, reveals a universe far stranger than we once imagined. We have journeyed from the missing blazar problem and the tantalizing whispers of dark matter, through the diffuse glow of star factories and the steady ticking of ancient pulsars. We have considered the faint echoes of galaxy clusters, the high-energy excess that defies prediction, and the profound smoothness that hides the universe's lumpy nature. We have peered into the magnetic labyrinths between galaxies, listened for the pure note of an annihilation line, and even searched for the fading fossils of the first stars and black holes. Each mystery is a thread, and together they form the gamma-ray background, not as a single enigma, but as the collective signature of everything the universe does in the dark. It is the sum of its most violent histories and its most subtle physics, a projection of all we know and all we have yet to discover. This story is not finished. The next decade of observation, with revolutionary telescopes now being built, will begin to pull on these threads. It will resolve the fog into countless points of light or reveal an irreducible glow that points unequivocally to new physics. These future discoveries will not just solve a puzzle, they will rewrite our textbooks on particle physics, cosmic evolution, and the very nature of reality. The greatest lesson of this journey is that the sky is not silent. It is speaking in a language of unimaginable energy, and we are only now learning to translate its first words. Which of these 25 mysteries captures your imagination the most? Is it the ghostly signal of dark matter, the unified roar of primordial black holes, or the magnetic skeleton of the cosmic web? Share your thoughts below and subscribe to join us as we continue to explore the deepest enigmas of the cosmos.